In 1925, Albert Einstein confided in a student, expressing his deep yearning to fathom the mysteries of the universe. While walking together, he shared, "I aspire to comprehend the manner in which God crafted this world. My focus lies not in the particulars of specific phenomena or the intricacies of elemental spectra. What truly captivates me is gaining insight into the divine thoughts behind it all. The rest, mere intricacies." This singular conversation encapsulates the essence of Einstein's overarching philosophy, a philosophy that has impelled humanity to explore, uncover, experiment, and, above all, expand its knowledge of the universe we call our home. Yet, what exactly did Einstein mean by his words? And is it ever conceivable for human knowledge to attain a level where we grasp the entirety of existence? Since the unveiling of the realm of quantum mechanics in the early 20th century, scientists have been tirelessly grappling with the quest to unravel its inner workings. Even after the passage of a century, we find ourselves in a state of uncertainty regarding the mechanisms governing the behaviors of subatomic particles and the rationale behind their actions. However, this represents merely one facet of the challenge at hand. The advent of quantum theory has introduced a more profound conundrum, one that has engaged the dedicated efforts of luminaries such as Einstein, Stephen Hawking, and other globally acclaimed physicists who have devoted themselves to its resolution. The primary challenge can be encapsulated in a single term: unification. In the realm of contemporary physics, we encounter a division into two fundamental frameworks. Firstly, there is classical physics, as expounded by luminaries like Newton, Einstein, and Galileo. This branch aptly forecasts the forces of gravity and elucidates the movements of substantial entities, such as celestial bodies, including stars and planets. Secondly, we have quantum physics, governing the behavior of subatomic particles, operating by its distinct set of principles and laws. Both paradigms provide accurate descriptions of their respective domains, but falter when applied to the subject matter of the other. Einstein's foremost concern was to find a means of harmonizing these two disparate worlds. He sought a theory that could reconcile the subatomic realm with the macroscopic one, a theory endowed with the capability to predict, in essence, all phenomena. You might be pondering, why is this significant? The rationale behind its importance lies in the prospect that a comprehensive theory capable of bridging these two domains could conceivably reveal numerous enigmas about our universe. Moreover, it has the potential to address some of the most profound philosophical and theological inquiries that have intrigued us since the era of Galileo. Questions such as the very composition of our existence, the events preceding the Big Bang, and the potential existence of a multiverse could find resolution through the lens of the unified theory, often referred to as the theory of everything. In essence, this theory could hold the key to elucidating all of these profound inquiries. The entire cosmos, along with its constituent elements, is intricately held together by four primary forces when it comes to substantial entities such as stars, planets, humans, and cats. Their interactions are predominantly dictated by the force of gravity. Remarkably, thanks to Einstein and his groundbreaking general theory of relativity, we've come to realize that gravity is not merely a mystical force that mysteriously draws objects together. Instead, it manifests as the curvature and distortion of the very fabric of our universe, what we call space-time. While this single fundamental force governs the behavior of all these substantial entities, subatomic particles, in contrast, adhere to the influence of three distinct fundamental forces, adding yet another layer of complexity to their behavior, as if they weren't already perplexing enough. The three fundamental forces are electromagnetic, weak nuclear, and strong nuclear. Electromagnetism binds atoms. The strong force binds nuclei, and the weak force governs certain nuclear decay processes. These particles and their associated forces constitute the Standard Model, which explains the subatomic realm. Everything in the universe, including celestial bodies, humans, and animals, consists of subatomic particles. All matter is composed of atoms, comprising protons, neutrons, and electrons. In the 1960s, we revealed that protons and neutrons are composed of quarks, while electrons are a type of lepton. By employing various combinations of these particles and their associated forces, we construct entities such as atoms, molecules, humans, planets, and even stars. Hence, the Standard Model appears to be a comprehensive framework for understanding our universe. However, it falls short in one aspect. The quest for the tiniest subatomic particles represents merely the initial phase toward formulating a theory of everything. The subsequent challenge involves incorporating gravity into this model. There are two primary reasons why gravity remains unaccounted for in this context. Firstly, gravity's influence on quantum systems is exceedingly weak at the scale of small particles, rendering it negligible. Secondly, the integration of general relativity, which describes the motion of massive objects, with the quantum realm governing subatomic particles, remains a formidable challenge. Numerous notable minds, including Einstein, dedicated relentless efforts to this endeavor. Even on his deathbed, Einstein reportedly revisited his notes on the theory of everything, striving for an elegant solution to reconcile the fundamental disparities between the micro and macro worlds. Unfortunately, time eluded him. However, while a comprehensive theory eluding us, substantial strides have been taken, with one remarkable breakthrough credited to the brilliant Stephen Hawking. In 2014, a movie depicting the remarkable life of Stephen Hawking was released, elevating him to the status of one of the most revered physicists globally and a beloved figure in popular culture. However, behind the public spotlight, Hawking, much like Einstein, possessed an insatiable thirst for comprehending the universe and consistently pushed the boundaries of our knowledge. One of his most significant contributions was the identification of what we now refer to as Hawking radiation. In 1974, Hawking made a groundbreaking breakthrough that reshaped our understanding of black holes and established an unprecedented connection between the realms of quantum mechanics and gravity. Hawking's discovery was so ingenious that it instilled hope that achieving the theory of everything, the ultimate goal of physics, remains within the realm of human possibility. Black holes, densely concentrated regions of space, possess an overwhelming gravitational force that prevents anything, even light, from escaping. Einstein's 1916 general theory of relativity first predicted the existence of black holes, and in 1974, we substantiated these predictions by observing our first Milky Way black hole. In that same year, Hawking made a groundbreaking revelation. Black holes can, over time, dissipate and emit energy, a phenomenon now termed Hawking radiation. But how can energy escape from a black hole when nothing else can? Hawking elucidated this using quantum principles. Although we typically envision space as vast, cold, and desolate, it teems with dynamic energy generation and annihilation processes at the subatomic level. Particles, including matter and antimatter, continually form and annihilate in pairs. Hawking envisioned a scenario where such a particle pair materializes very near the event horizon of a black hole, the point beyond which nothing can break free. He demonstrated that these particles need not annihilate each other, as one of them can be drawn into the black hole. If the black hole is acquiring negative energy, it must consequently emit energy to uphold the law of energy conservation. Hawking's work also established that black holes progressively lose mass over time and are not eternal entities. Crucially, he achieved this breakthrough by bridging quantum principles with the concept of gravity. This marks the closest we've come to attaining a theory of everything, a unified field theory, or quantum gravity. However, in the realm of science, the absence of a single elegant equation does not equate to failure. Instead, it underscores that the true treasures lie in the discoveries we've made along the journey, many of which pave the path toward a brighter future for humanity. String theory stands out as one of the most prominent theories in physics. It proposes that subatomic particles, including electrons and quarks, consist of minute vibrating strings or filaments that twist and fold, giving rise to the entirety of our universe. Similar to the strings of a violin, these strings can vibrate in various patterns, generating diverse particle types, including the graviton, a theoretical particle that, according to quantum mechanics, should convey the force of gravity. On paper, string theory has the potential to unify gravity and quantum mechanics within a single framework conclusively. This theory gained popularity during the 60s and 70s, and its mathematical framework predicts the existence of compact extra dimensions, which could lead to a network of universes or a multiverse. However, it's important to note that while string theory is prominent, it remains exceptionally challenging to test, even with the most advanced technology at our disposal. Nevertheless, string theory represents just the initial step. After nearly 2 decades of exhaustive research, we succeeded in discovering the Higgs boson. This breakthrough demonstrated that electrons and quarks within atoms acquire their mass from an invisible field that permeates space. The discovery was the result of the dedicated efforts of a group of 3,000 scientists who invested countless hours in a quest that brought humanity closer to comprehending our universe. Our exploration has revealed a startling fact. All the atoms and light in the universe constitute less than 5% of its total content. The remaining 95% is comprised of dark matter and dark energy, both invisible yet wielding paramount influence over the universe's evolution. Dark matter exerts gravitational forces that bind galaxies together, while dark energy propels the universe's relentless expansion. For millennia, humanity has gazed skyward, pondering the enigmas concealed beyond the celestial veil. Since 1970, NASA and the ESA have launched over 90 telescopes into orbit, bridging the cosmic gap and bringing the universe closer to us. And with the James Webb Telescope that launched on December 25, 2021, we entered a new era of discovery. The James Webb Space Telescope, the largest and most potent telescope ever constructed, bears the formidable responsibility of locating the initial galaxies that emerged in the early universe. It also aims to penetrate dusty veils to observe the birth of stars and the formation of planetary systems. While the unification of quantum mechanics and gravity remains elusive, each discovery we make propels us one step closer to achieving this ultimate goal of unification. Throughout our tenure on Earth, we've continually pushed the frontiers of understanding by posing challenging inquiries and dedicating ourselves tirelessly to uncovering solutions. As a species, we've been characterized by our insatiable quest for knowledge and an enduring belief in the concept of a unified universe. It's been 350 years since we took a significant stride in this ongoing voyage, marked by Newton's unification of the celestial and terrestrial realms. His revelation, demonstrating that planets, stars, and falling apples adhere to the same fundamental laws, has left an indelible mark on our exploration of the cosmos. 2 centuries later, James Clerk Maxwell intertwined electricity with magnetism. While Einstein fused space and time into a single entity we now call space-time. Examining this chronological progression, it becomes evident that the path forward may be considerably protracted. Einstein departed this world with visions of a unified set of physical laws governing our reality, an overarching framework capable of unraveling the enigmas of the cosmos. Hawking, too, continued to gaze at the stars, pondering the untold mysteries awaiting discovery. Whether the quest for a theory of everything is a pragmatic pursuit or a quixotic endeavor aimed at making sense of the universe's surreal complexities, one truth remains constant. Our unyielding faith in the pursuit of unification serves to propel humanity forward in its evolution as a species. If you feel you are in a black hole, don't give up. There's a way out.